Guys, here's homework solutions for 1.4. So for number 1, sorry things got bunched up together. So for number 1, we're trying to find the intervals where we are increasing, decreasing, or constant. So my graph is getting bigger from negative infinity to 0. So from negative infinity to 0, we're increasing. And then also, so then when you start decreasing, and then right here, let's say about what, 1.3-ish? 1.3-ish, we start increasing again. So 1.3 to infinity, which means we have to be decreasing in the middle. So between 0 and 1.3, we're decreasing. That's this portion here. For number 2, where are we increasing? So going from left to right. Remember, you read your graphs always left to right like a book. So left to right, I'm going down, I jump up, and I'm going down again. So we're not increasing anywhere. We can't say we're decreasing everywhere because this is a rational function, which means I've got this asymptote here. So I have to say from negative infinity to 0, and then from 0 to infinity, because at 0 we're not increasing or decreasing, we have an asymptote there. All right, number 3, estimate to the nearest 0.5 unit. Oh, it did say 0.5. Did it say 0.5 up here? So this hair's not paying attention? Yeah, it says to the nearest half unit. So here we could probably say 1.5 instead of 1.3. Sorry about that. All right. For number 3, it also says estimate to the nearest half unit and classify the extreme of the graph of each function. Support your answers numerically. I'm not too worried about supporting your answers numerically. Really, I just want you to be able to identify. So if we are looking for a maximum for number 3, I don't have an absolute max because it goes on to infinity. I do have a local maximum. And that's down here, where I've got that little hill. So that would be a local max value. Remember, the value is always your y value, and that would be roughly negative 4.5. And that's when x equals 0. And then for our minimums, I do have an absolute minimum this time. This is the absolute lowest part of my graph. So I can say an absolute minimum. And that value, let's see, that's negative 4. So 2, 4, 6, 8, plus a little bit. So let's say negative 8.5 at x equals, let's see, that'd be, the scale's different over here. So 1, 2, 3, 4. So at negative 1.5. So when I went and looked at the scale, I realized we got our y-intercept wrong. If this is 2 and this is 4, this would have to be 5, not 4.5. Interesting the way they scaled this graph differently for your x's than for your y's. All right, so that took care of our absolute minimum. We also have this little local minimum over here. That value, let's see if we can figure out the scale this one. 2, 4, 6 would be at negative 6. So local min value of negative 6 at x equals 1 there. Roughly, more or less. All right, number 4. I don't have an absolute maximum because this guy goes up to infinity. I do have a local maximum here. So I have a local max of 1 at x equals negative 1. I don't have an absolute minimum because it goes down to negative infinity, so there's no bottom point, but there is a little local minimum right here. And since we're supposed to round to the nearest half, let's just call that of, it's below the x-axis, so I'm going to say of negative half. I think it's probably closer to 0, but that's kind of misleading. So local minimum of negative half at x equals positive half. You could argue that would be 0, because it is closer to 0. All right, it says on the graphing calculator approximate to the nearest hundredth the relative or absolute extreme of h of x is equal to x to the fifth minus 6x plus 1. So I'm going to do this on Desmos because that's what I tell you guys to use for your graphing calculator because you don't have Inspires at home. So let's see what that would look like. Maybe if I can get another tab pulled up here. So it's desmos.com, desmos.com. This is what the landing page looks like. We're just going to start graphing. And then from here, we wanted it to be x to the fifth minus 6x. So x to the fifth. And then minus 6x, then that's 5. Let's see if we got that right. X to the fifth minus 6x, plus 1. X to the fifth minus 6x plus 1. All right, here's our graph. So notice how it gives you just about everything you have on your TI Inspire. It's actually kind of nicer because you can just squeeze it. You don't have to worry about zooming in or out. You don't have to remember what the commands are to find the maximum. You can just use your little slider down here and you'll get down to the bottom point. You see that's at 1, -4. My top point up here. Where did we go? What does that look like? -1,6. So I've got -1,6 and then 1, -4. So that means we have and notice on this graph, it goes down to -30, up to positive infinity. So no absolute max or min. We've got a local maximum here at -1,6. So I have a local max of 6 at x equals -1. And then we have a local minimum. The minimum was over here. Well, let me draw on this just so you know. And that was at 1, -4. So the value of our local minimum is -4 at x equals 1. All right. Number 6 asks us to find the average rate of change of each function on the given interval. So we want to find f of our second x value minus f of our first x value. And I'll get my second x value minus my first x value. In order to do this, I need to figure out what is f of -2. And we're plugging it into this function here. So I've got -2 to the 4th plus 2 times -2 squared minus 5. -2 to the 4th would be positive 16. -2 times -2 is 4 times 2 is 8 minus 5. So this is 24 minus 5 would be 19. And I also need to know what is f of -4. Let's try to squeeze it in here. So f of -4 would be -4 to the 4th plus 2 times -4 squared minus 5. Let's see, -4 times -4 is 16 times -4 is -64. 64 times 4, I don't have quite memorized. That'd be 256. So -4 to the 4th would be positive 256. 4 times 4 is 16, times 2 is 32, minus 5. So 256 plus 32 is 288, minus 5 would be 283. So here we've got 19 minus 283 all over -2. Remember, negative times a negative makes this plus 4. 19 minus 283 would be -264. 4 minus 2 would be positive 2. So 264 divided by 2 is 132. So minus 132. We have a lot of room for that one. Only thing I see wrong with what I just did is it gave us 6 in terms of g's, and I started writing them in f's because that's what we have most of the time. So that really should have been g of -2, g of -4, but same answer there. All right, let's look at number 7. This time I will do it with the proper terminology. So g of 6 minus g of 2 all over 6 minus 2. G of 6 would be -3 times 6 cubed minus 4 times 6. G of 3 is -3 times 3 cubed minus 4 times 3. So 6 cubed, which I should have memorized, is 216 times -3 would be -648. -6 times 4 is -24. So that's -672. And then 3 cubed is 27 times the -3 would be -81. -4 times 3 is -12. So that's -93. So I've got -672 minus a -93 all over 6 minus 2, which is 3. So we've got -672 minus a -93 would be +93, which gives us -579 divided by 3. And that gives us -193. Final answer for our arbitrary change there. We're going to do one more on this video, and then I'll flip to the word problem practice. So in physics, the height t in seconds after this toy rocket is launched straight up can be modeled by this function. Remember when we were talking about these arch-like functions, that -16, that's your gravitational factor of some sort. So -16 t squared plus 32t plus 0.5, where h of t is in feet. Find the maximum height of the rocket. So this is just a quadratic function, and we talked about this yesterday. To find the maximum, we want to find the vertex of our parabola. The vertex occurs where we've got that axis of symmetry, and that's where x is equal to minus b over 2a. So for this one here, it's going to be minus 32 all over 2 times a, which is -16. So that's -32 divided by -32, which is 1. Can't leave it just as 1. What are we talking about? We're talking about 1 second, right? So at 1 second, this toy rocket has reached its maximum height. All right, that's it for the first side. I will do a video for the second side now.